Hello grade 11 GED 2019-2020 students. We are in this third topic still, oscillations. Today we have lesson 3.2 and 3.4 as in your syllabus. Energy in simple harmonic motion. This is the third lesson for simple harmonic motion, and we have also damped oscillations and resonance. Objectives are to use the equations for kinetic potential and total energy for simple harmonic motion. Describe graphically the interchange between kinetic potential and total energy during simple harmonic motion. Apply the conservation of energy in simple harmonic motion. Define damped oscillations and describe practical examples. Define and describe practical examples of resonance. So, okay, kinetic energy in simple harmonic motion. Now, we have seen before that the velocity in simple harmonic motion can be given by this equation, v equal to plus or minus omega root square of x naught square minus x square, where omega is the angular frequency, x naught is the maximum displacement, which is amplitude, and x is the displacement at any time. So this will give us the velocity in terms of displacement. Now, as we know, for the kinetic energy, we have half mv square. So substituting v from here, we will get half m, and we will square the velocity here, so it will be omega square. We will get rid of square root, so x square, x naught square minus x square. So this is the formula, half m, where m is the mass for the oscillator, omega is the angular frequency. Now x naught is the amplitude, which is the maximum displacement from the equilibrium position, and x is the displacement at any time. Now, if we go back to this equation, for x equal to 0, for example, if we have the mass spring system, here is our spring with mass equal to m. If this is the equilibrium position, so when it is displayed at a distance of x naught here, and we know that this is the maximum displacement, x naught, which is a vector quantity away from the equilibrium position. Now, at x equal to 0 here, at equilibrium point, if we are going to substitute here x equal to 0 at equilibrium point, so you will get half m omega square x naught square, so which will be the maximum value for the kinetic energy. So here, when x equal to 0, the kinetic energy will be half m omega square here. This is 0, so we are left with x naught. This is the maximum value for the kinetic energy here when x equal to 0. Now for x equal to x naught here, if x equal to x naught, going back to the equation, when substituting here x with x naught, we will get x naught square minus x naught square, so E equal to 0, kinetic energy equal to 0. That's why here we have at x equal to x naught, kinetic energy is equal to 0. Also on the other side, equal to 0, we will substitute by minus x naught all square, so it will be 0. And here when x equal to 0, our kinetic energy is maximum, which is half m omega square x naught square. And it is the same for potential energy without any mass. Okay, so the potential energy is half m omega square x square, where m is the mass and omega is the angular frequency, x is the displacement at any time. So this will give us the potential energy. Now let's come here to our graph. At x equal to 0 here, equilibrium point, so all this will become 0, we will get 0 potential energy. When x is equal to x naught here, so at maximum displacement, or x equal to x naught, this leads to potential energy equal to half m omega square x naught square. This is the maximum value here for the potential energy. So when you go back, like here, we have the value for kinetic energy equal to 0, since the velocity at the point, these points is equal to 0 at maximum displacement. At equilibrium point, the velocity has the maximum value, so we have the maximum value of velocity. Now, maximum value of velocity here at equilibrium gives the maximum value of kinetic energy, which is half m omega square x naught square. We will find that this is the same value of potential energy that we are getting here in the maximum displacement. Here, the same value we are getting for potential energy, but here, when x equal to x naught. So going to the expression for the total energy, the total energy is equal to the kinetic energy plus potential energy. At any point, energy is conserved. So substituting kinetic energy by half m omega square x naught square minus x square, plus this is the potential energy and this is the kinetic energy, and we have a common factor that is half m omega square, and minus x square will cancel with positive x square, and we will end with half m omega square x naught square. So this is the total energy, half m omega square x naught square. Now, again, coming to the graph, you found that this is the same value of kinetic energy at x equal to 0 here. At x equal to 0, kinetic energy is maximum, the same value. And it also gives the value for potential energy at maximum displacement when x equal to x naught here. So this is the curve for potential energy, this is the curve for potential energy where the energy is equal to 0 at equilibrium point and maximum at x equal to x naught. So here, at any point here, the kinetic energy plus the potential energy will give us the constant value here of total energy, which is half m omega square x naught square. So if you come here, kinetic energy equal to 0, but potential energy here, kinetic energy equal to 0, but potential energy is maximum, which is equal to half m omega square x naught square. So the sum of them will give us the total energy. When we come here, our potential energy equal to 0, but our kinetic energy is maximum, which is maximum kinetic energy, which is again equal to half m omega square x naught square. So the sum of them will give us the total energy. And it is the same at any point. At this point here, or this displacement, the energy, kinetic energy, will be equal to the potential energy. Half of the total energy is kinetic and the other half is potential, and the sum of them will give us the total energy. So this is the energy in simple harmonic motion. As you see, kinetic and potential energy, they are changing with displacement. So this is the x-axis, which is giving us the displacement, and y-axis will give us the energy. Now let's do some questions. A particle of mass or an object of mass 0.4 kg, so we have a mass of 0.4 kg, which is oscillating in simple harmonic motion with frequency of 5 Hertz. Always you have to write the given. And amplitude of 12 centimeters, so we have x naught equal to 12 centimeters. Which is 0.12 meters. We are talking in terms of energy. Energy is in joule, so all the other quantities should be in the SI units. Calculate for the particle or the object the displacement at displacement 10 centimeter. So we have displacement of 10 centimeters, which is 0.1 meter, they are asking about the kinetic energy, potential energy, and the total energy. So let's go write the equation for kinetic energy, which is equal to, at any distance, it is half m omega square x naught square minus x square. Substituting half, our m is 0.4, our omega is, okay, now we have to calculate omega. We have F, so we can calculate omega related to F by 2 pi F, so it is 2 pi times 5, which gives us 31.42 rad per second. So put it here. We have 31.42 all square and time x naught square, which is 0.12 square, minus x square, which is 0.1 square. This will give us the value for kinetic energy at 10 centimeter or 0.1 meter, and it should be 0.87 joules. Part B is asking for potential energy. So potential energy is, now don't forget that our amplitude is 12 centimeters. So what we have here all is 12 centimeters. Now our displacement is 10 centimeters. It is about to be here. So we have our potential energy, which is equal to half m omega square x square. So half times 0.4, the value of mass, time omega square, we have it 31.42 all square, time x square, which is the displacement, 0.1 square. This will give us the value for potential energy at this displacement, which is 1.97 joules. So if you come here at this displacement, kinetic energy equal to potential energy, but what we are getting, our potential energy is greater than the kinetic energy. So we are somewhere here. Potential energy has the distance value more than kinetic energy. So we are somewhere here, close to the 12 centimeter. And the sum of them will give us the total energy. So total energy will be the sum of the potential energy and the kinetic energy, which will be 2.84 joules. This is another question. A mass of 0.2 kg, oscillating in simple harmonic motion. The energy displacement graph is shown. Calculate the frequency of the motion. Now, this is energy with displacement. The maximum displacement, which is the amplitude, is 15 centimeters. Now, what we are asked to calculate the frequency for the motion. This seems to be the curve of kinetic energy when it has the value of the maximum value at equilibrium point and 0 at the maximum displacement. So this is the maximum value for kinetic energy, which is the value for the total energy. Maximum value here is the also because the potential energy here is 0, so the maximum value for kinetic energy will give us the total energy. So we can apply either kinetic energy equation or total energy equation. So we can write our total energy equal to half m omega square x naught square. Even if we are taking the value of kinetic energy, which is half m omega square x naught square minus x square, we have here at x equal to 0 the maximum value, which will be also the same as the total energy. So it will lead to the same equation. So what we have to find here, we have the total energy, 3.5 joules, which is equal to half times m, our mass is 0.25. Here we have our omega square. Then we have our maximum displacement, 15 centimeter, which is equal to 0.15 meters. So this is 0.15 whole square. This will give us the value for omega. So we can find omega, which will be 35.28 rad per second. From here, you can find the value of the frequency by applying omega equal to 2 pi f. F will be omega over 2 pi, so you will divide 35.28 over 2 pi. This will give you the value of for the frequency in hertz. This was the end of kinetic potential and total energy for simple harmonic motion. Now we will go to free and damped oscillations. A particle is said to be oscillating a free oscillation when only external force on it is the restoring force. So, like when we talked about a simple pendulum and we considered that the restoring force is acting on the object When it is away from the equilibrium position, it will try always to return the object back to the equilibrium position. So this was a kind of free oscillation. But so theoretically, the oscillations can go forever because no energy is escaping out. The object here will oscillate with the same amplitude. This is the displacement time when we draw the displacement time graph. It will be like this, same amplitude and frequency. But in reality, in practice, something else will happen. Oscillations cannot go forever. Okay? Why? Because frictional and other resistive forces cause the oscillator's energy to be dissipated. When the energy is dissipating, so it can be converted into thermal energy, for example, because of the friction. Then the oscillation is said to be damped. As we have here, a damped oscillation, the amplitude is decreasing with time. Like what will happen here if a child is swinging, okay, with any external force, after a while it will come to stop. But it's very important to know that the frequency is constant here. It is a characteristic of the body with simple harmonic, which is vibrating in simple harmonic motion, or even here for a damped motion. But the amplitude will decrease. So coming to the example of the child, for example, if you have here a swing and a child here, okay, so a child on a swing, the amplitude will decline until the child come to rest. Unless if more energy is added, yes, to the system, then it can continue swinging. Because energy here, usually energy is escaping to surroundings. Why this is happening, as we said, because of the friction. There is a friction with the frame. There is friction due to air resistance. So this oscillation is damped oscillation. The amplitude of the oscillation will decrease till it stops. Now, the amplitude can decrease rapidly or gradually, but it does not change linearly. This is the curve which is showing how the amplitude is changing. So the amplitude is changing exponentially with time. At first, the swing moves rapidly because there is a lot of air resistance. So the swing loses energy quickly. So when we have more air resistance, it means energy loss quickly. So the amplitude decrease at higher rate. From here to here, see the rate of decreasing. So amplitude will decrease at higher rate. But with time, what will happen that it is moving more slowly. So the air resistance, so the energy loss is less. So it is moving more slowly, air resistance less, energy loss is less. That's why the rate of changing energy is less. So this is why the change in displacement or the amplitude is change in amplitude is forming an exponential curve with time. Now, damping, this is because damping can be useful. Like if we want to get rid of vibration, for example, in vehicles they have springs between the wheels and the frame to give smoother ride. For us, when a car goes over a bump, these springs help so that we can ride more smoothly. Otherwise, we will keep vibrating up and down. So this is an example of useful damping. Also, we have swing doors. Swing doors have a damping mechanism. The purpose of the damping is so that the open door, when released, does not overshoot the closed position with the possibility of injuring someone who is approaching the door. So here damping is very useful. We want the door to be closed with no oscillations. So it should come at its equilibrium position as fast as it is possible in less time. That's why the door should be designed in such a way that it is correctly damped without swinging several times before stopping, with critical damping here. With critical damping, it will come here to the position of zero displacement in less time without any oscillation. So critical damp is the minimum amount of damping need to return the equilibrium without oscillation. This is the critical damp. So it is the minimum amount of damping need to return the equilibrium position with no oscillation. If here for overdamp oscillation, the time to stop or to come to the equilibrium position will be greater. So these are some useful examples of damping. Now, force oscillations and resonance. When a body is vibrating undergoes free oscillation. So for a free oscillation with no damping, the body vibrates with its natural frequency. But if an external, natural frequency, it means the only force is there, the restoring force. But if any additional force acts on the body, so this force will make the object vibrate at the frequency of the applied force. If the body is not vibrating in its natural frequency, but it is vibrating at the frequency of the applied force, then we say that the body or the object is undergoing force oscillation. So this is force oscillation. When an external force other than the restoring force acting on a body and making the body to vibrate with the frequency of that applied force, not its own natural frequency. We have here, resonance. When the natural vibrating frequency equal to the driving frequency, so we have the natural frequency of the body and we have the driving frequency if there is any external force. If the vibration of the frequency equal to the driving frequency, so resonance will take place here. So this is the definition of resonance, which is a phenomena occurs when the natural vibrating frequency of the body equals to driving frequency. Resonance always makes the body vibrate with maximum amplitude. Now this is the resonance curve. This is amplitude and this represents the driving frequency. So if anybody, anybody is affected by a force, so when the natural frequency of the object equal to the driving frequency, here resonance will occur. So the body will start moving with maximum amplitude. At this position, at this frequency, this is the resonant frequency. It means the body or the object is vibrating or reached a point at that the frequency of the body equal to the driving frequency. This also shows the effect of damping on resonance. Now, more damping will make the amplitude to decrease. So the amplitude is decreasing with heavy damping. Now let's take some examples of resonance. We have the Millennium Footbridge in London. Up to 2000, when over 2000 pedestrians were walking on the bridge, and this bridge in 2000 June, it started to sway and it was closed. Also, the people walking on this bridge swayed. So engineers analyze the problem here, and they found that this happened because the problem of the phenomena of resonance. The bridge was vibrating with its maximum amplitude because its natural frequency was equal to the driving frequency, external frequency. So it starts moving or vibrating with maximum amplitude because of resonance. So this problem was solved by adding some dampers just to absorb the energy of oscillation, so the amplitude will become, so it cannot vibrate with that high amplitude. And another example is the Barton's pendulums. We have here different length pendulums with very light masses here, like paper cones, and this is another pendulum which is much more massive. So this is the driver. When this driver pendulum starts swinging, of course, gradually all these will start vibrating, but only one of them will vibrate with maximum amplitude. The one which is vibrating with the same frequency of the driver because of resonance. So which one can vibrate with the same frequency? As we know that time period for pendulum equal to 2 pi root square of L over G, and we discussed this point last lesson. So we know that the and T equal to 1 over F. So because T depends on the length of pendulum, that's why the frequency also depends on the length of pendulum. So if they have the same length, so they should have the same frequency. So if this pendulum has a certain natural frequency, it will start vibrating with the same frequency of the driver pendulum. So this will make this pendulum to move with maximum amplitude, and this is because resonance. Now we came here to the end of our lesson. Thank you.